Hello everyone, this is the first part of the lectures devoted to cross-coupling reactions. We will start this module with a general introduction describing the importance and history of cross-coupling chemistry. Let's begin with some definitions. What type of transformations can be called cross-coupling reactions? There are many interpretations for that, and the most common explanation states the following. In organic chemistry, a cross-coupling reaction is a reaction where two fragments are joined together with the aid of a metal catalyst. Here is a general reaction scheme describing cross-coupling reactions. Most of the known cross-couplings involve highly significant carbon-carbon bond-forming processes. These are fundamental transformations, as the molecules of life are predominantly based on carbon-carbon bonds. As a rule, the reaction is based on the coupling of a main group organometallic compound, shown in red, with an organic halide, shown in blue. The reaction is enabled by late transition metals, which normally operate in combination with bulky and electron-rich ligands. The most frequently used catalysts are based on palladium. If your organometallic compound is an organoboron or an organosilicon reagent, then for their activation, you will need a base. Most of the cross-couplings you will learn today are name reactions and are defined by the used nucleophilic coupling partner indicated in red. For instance, cross-couplings based on organoboron reagents are called Suzuki coupling. Reactions with organodine reagents are known as Stille coupling. When the nucleophile is an aniline, the reaction is called Buchwald-Hartwig amination. Most of the known cross-coupling reactions have very similar mechanisms. The generally accepted mechanism for palladium-catalyzed reactions is depicted here. It involves most of the elementary reactions we learned during the last module of the course. The reactions are normally initiated by palladium-0 complexes, which means that if a palladium-2 pre-catalyst is applied, it is reduced to its active form before entering the catalytic cycle. The reaction is initiated by the oxidative addition of the palladium-0 pre-catalyst to the aryl halide or pseudohalide, generating this palladium-2 intermediate. The next step can be slightly different for various cross-couplings. If the next coupling partner is an organometallic compound, then oxidative addition is followed by transmetallation, generating a palladium-2 intermediate bearing fragments from both coupling partners. The last stage of the process involves reductive elimination, resulting in carbon-carbon bond formation regenerating palladium-0 species, which can re-enter the catalytic cycle. Cross-couplings catalyzed by nickel or copper have more complex mechanisms and will not be covered in this lecture. To answer the question about why do we need to study cross-coupling reactions, we need to assess some numbers. This chart shows the number of publications and patents on the most common cross-coupling reactions over the last 3 decades. Color codes are used to differentiate the name reactions from each other, as depicted on the right side of the chart. For instance, the columns in dark orange show the number of publications on Suzuki coupling, while the black columns indicate the publications on Sonogashira coupling. As you can see, from the early 2000s, there has been exponential growth in the field. This growth is directly related to the design and implementation of new highly active catalysts and ligands, which will be discussed later in the module. This field of research is dominated by the studies on Suzuki coupling. Over the last decade, more than 20,000 works have been published, dealing in some way with Suzuki coupling. Between 2001 and 2011, the number of publications and patents on Suzuki coupling was more than 10,000. The second and third most popular transformations are Heck coupling and Sonogashira coupling, respectively. Other couplings are less popular but still grabbed considerable interest. In 2016, an interesting work appeared in the Journal of Medicinal Chemistry, which was about the analysis of past and present synthetic methodologies used in medicinal chemistry. In the work, the authors analyzed the most frequently used reactions in medicinal chemistry, covering the years 1984 and 2014. This chart summarizes the results of the study, where the red columns represent the occurrence and percentages of a given reaction in the year 1984, while the blue columns refer to the distribution of popular reactions in 2014. As you can see, the Suzuki coupling is the second most frequently used reaction in medicinal chemistry. 19% of the works published in 2014 cover the Suzuki coupling at least once. Buchwald-Hartwig amination and Sonogashira coupling are also in the top 20 most frequently used reactions for drug discovery. It is noteworthy that cross-coupling reactions had limited applications in 1984, as this field of research was still in its infancy. On top of the traditional cross-couplings, Amide bond formations and ester formations nowadays are frequently realized by carbonylative cross-coupling reactions. In this work, the authors raise another legitimate question. Where have all the new reactions gone? You see, medicinal chemistry predominantly is based on well-established and reproducible reactions, which exhibit good functional group tolerance. Unfortunately, these factors are not always inherent to the modern super-duper transformations published in the Journal of the American Chemical Society or other high-impact journals. Versatility, reproducibility, and the possibility to construct all sorts of carbon-carbon and carbon heteroatom bonds are perhaps what made this field so popular and eventually led to the Nobel Prize award in chemistry for the year 2010. Now, we can go through some history and see how this field of research has emerged and evolved. In addition, I will guide you through specific details of some cross-coupling reactions. The development of cross-coupling chemistry conventionally can be divided into 3 periods. The first wave of developments involved the discovery of cross-coupling as a concept, the first attempts to realize this chemistry in a selective fashion, and the elaboration of the first catalytic transformations. This spanned more than a century, from 1869 to 1976. The second wave of developments took almost 2 decades and was focused on the expansion of the scope of coupling partners. This was the period when more versatile organometallics based on metalloids were introduced. The third wave of development started in 1995 with the discovery of the Buchwald-Hartwig amination and is still in progress. Here, the main focus of the research was and is on the continuous improvement and extension of known cross-couplings through rational design and fine-tuning of ligands. This chemistry is older than you could possibly imagine. It has a rich and intriguing history with some of the oldest transformations in organic chemistry dating to the 19th century. The earlier discoveries in the field were the metal-mediated homocoupling processes between 2 structurally identical fragments, which set the foundation for the later discoveries. Cross-coupling chemistry began in 1869 when Glaser described the oxidative dimerization of a previously prepared copper phenylacetylide to give a diphenyl diacetylene in an open flask. Following the development of homocoupling of sp hybridized systems, the copper-mediated methodology was extended to carbon-carbon bond-forming reactions of sp2 hybridized systems. In 1901, Ullmann reported the dimerization of 2-bromo and 2-chloronitrobenzene promoted by the use of superstoichiometric copper powder. The key difference between the Glaser dimerization of acetylenes and the Ullmann homocoupling is that the latter is based on the use of pre-functionalized or halogenated systems. The use of halogenated organic molecules turned out to be a common theme for the following developments in the field. Later, in 1914, Bennett and Turner demonstrated that Grignard reagents also can be dimerized in the presence of stoichiometric quantities of chromium-3 chloride. A few years later, Turner also reported an analogous homocoupling reaction promoted by copper-2 chloride. Despite these remarkable achievements, the early metal-promoted reactions were limited in 3 key ways. First, stoichiometric metal reagents are poorly soluble in common solvents because of that the reactions are slow and require harsh conditions. Second, the reactions are not selective. And finally, the reactions include pyrophoric reagents and demonstrate poor functional group tolerance. The first glimpses of a solution to these issues appeared during the first half of the 20th century. Although catalytic quantities of copper had been shown to promote the carbon-oxygen coupling reaction of phenols with aryl halides as early as 1905, the use of catalytic amounts of metals for the formation of carbon-carbon bonds somehow remained an elusive concept during the first part of the 20th century. In 1939, Meerwein was the first to report the effects of catalytic copper-2 salts on the coupling of aryl diazonium salts with cinnamic acids. However, Meerwein's groundbreaking studies appear to have been lost in time, and even now there are only 226 citations of his work. The first systematic investigation of transition metal-catalyzed carbon-carbon coupling is found in a 1941 publication by Karash, which describes the cobalt-2 catalyzed coupling of Grignard reagents with aryl halides. In subsequent studies, this work was extended to the cross-coupling of vinyl bromide with aryl organomagnesium species. These studies represent not only the earliest reports on catalytic cross-couplings but also the first selective carbon-carbon bond-forming reactions based on 2 different coupling partners. After this point in the history of coupling chemistry, a set of standard requirements for coupling processes became apparent. In the broadest sense, any coupling procedure required 3 components to achieve a selective cross-coupling event: an organohalide, as a coupling partner, a stoichiometric organometallic partner, to prevent homocoupling of the organohalide coupling component and a transition metal in catalytic quantities to affect the carbon-carbon bond forming event. These components would prove to be the guiding principle in coupling chemistry to this day. The utilization of palladium-based catalysts significantly facilitated the developments in the field and set the grounds for the discovery of other important cross-couplings. Palladium was discovered by Wollaston more than 2 centuries ago, but all the efforts from Wollaston to get a profit out of palladium were unsuccessful. The first catalysts on palladium were palladium on charcoal and Lindlar catalysts. These catalysts are used for selective hydrogenations of unsaturated systems and are commonplace in research laboratories even today. As a result, it quickly became evident that catalysts on palladium demonstrate high affinity and activity for double and triple bonds. The first palladium-catalyzed cross-coupling was the arylation of olefins, which is frequently called Heck coupling. In the late 60s, Richard Heck was employed in a company heavily invested in the commercialization of the palladium-catalyzed oxidation of olefins, known as the Wacker process. This is where he got interested in the potential application of olefins and palladium catalysts for the development of a new cross-coupling reaction. The first successful results came when he treated organomercury compounds with olefins in the presence of a palladium catalyst and air. It was clear that due to the high toxicity of the organomercury reagents, alternative procedures are highly desired. As a result, a few years after Heck's initial report, it was demonstrated that aryl halides also can be successfully olefinated with palladium catalysts. The new methodologies required stoichiometric amounts of a weak base and an inert atmosphere. Over the following decades, a vast number of groups would demonstrate the high functional group tolerance and wide applicability of the new methodology. Presently, the Heck coupling has a unique place in the arsenal of methods available for organic synthesis. The mechanism of Heck coupling is slightly different from other couplings. Among the known cross-couplings, only the Heck reaction does not involve a transmetallation step. The oxidative addition of the aryl halide to the catalytically active palladium-0 species initiates the catalytic cycle. At this stage, the processes diverge. In the Heck coupling, the reaction progresses by coordination of an alkene to the palladium-2 species, which is followed by a syn-migratory insertion. The regioselectivity of this insertion depends on the nature of the alkene, the catalyst, and the reaction conditions employed. The newly generated organopalladium species then undergoes syn-beta hydride elimination to form the alkene product. The active form of the catalyst is regenerated by reductive elimination of an acid, which is neutralized by the base. Until the mid-1970s, the field of acetylene coupling was dominated by the use of copper salts as catalysts. However, in 1975, the palladium-catalyzed coupling of acetylenes with aryl or vinyl halides were concurrently disclosed by the groups of Kasser, Heck, and Sonogashira. The coupling conditions reported by Sonogashira, employing copper co-catalysis, that made the reaction conditions exceedingly mild when compared to the copper-free methodologies from Kasser and Heck. The reaction demonstrates high functional group tolerance as it requires a weak organic base and mild conditions. Thus, the Sonogashira coupling is frequently applied as a late-stage coupling strategy in the synthesis of complex molecules. For the Sonogashira coupling, there are 2 catalytic cycles operating together. The deprotonation of acetylene is assisted by copper and leads to the in situ generation of the corresponding copper acetylide. The latter undergoes a transmetallation with the palladium-2 intermediate, regenerating the copper catalyst. The reductive elimination of the product from this palladium acetylide intermediate regenerates the palladium-0 catalyst, which can undergo another oxidative addition in the next cycle. It is important to highlight that the reaction is highly sensitive to air. In the presence of oxidants, copper acetylide intermediate instead of transmetallation can form notable amounts of a byproduct diacetylene via Glaser coupling. A common limitation of both organomagnesium and organolithium coupling partners was the inherent intolerance of sensitive functional groups due to the reactive nature of these anionic organometallic species. Thus, in the years surrounding Heck's discoveries, chemists sought to find less reactive anionic organometallic reagents. In 1977, Negishi and Juten reported the use of organozinc reagents in cross-coupling reactions. It was demonstrated that organozinc reagents can tolerate many functional groups, including nitro group and carbonyl compounds, which was unheard of for Grignard reagents. Subsequent findings indicated that magnesium and lithium could be replaced with other metals and some metalloids, which might be capable of participating in the proposed transmetallation step in the catalytic cycle involving palladium. The first metalloid demonstrating meaningful rates for transmetallation to palladium species was tin. The first report on the synthetic utility of organometallic reagents for cross-couplings came from the group of Mijita. They demonstrated that for palladium-catalyzed allylation of aryl bromides, one can apply allyl-tributylstannane. Later, the group of Stille unveiled the synthesis of ketones by coupling acyl chlorides with organostannanes under significantly milder reaction conditions than those reported by Mijita. In the early 1980s, Stille further explored and improved this reaction, developing it into a highly versatile methodology displaying remarkably broad functional group compatibility. This reaction was among the first cross-couplings used in total syntheses, which, in turn, changed the ways that chemists thought about carbon-carbon bond construction. Without argument, the main disadvantage of the Stille coupling is the toxicity of organostannanes. To address this issue, the studies on the development of alternative organometallic coupling partners were expanded further. Here, a short historical context can help us to understand better the process of the discovery of Suzuki coupling. In the early 60s, inspired by the research on hydroboration of unsaturated systems, Suzuki moved to the group of Herbert Brown for a short postdoctoral study. Herbert Brown was one of the founders of this field of research, which eventually was recognized by awarding the Nobel Prize in Chemistry in 1979. Organoboron compounds are quite different from other organometallic compounds. Compared to organomagnesium or organozinc reagents, they are chemically inactive, have low nucleophilicity, and rather behave like Lewis acids. Organoboron compounds are stable in the presence of water and alcohol and do not undergo typical Grignard-type reactions. Therefore, it was believed that such compounds would not be suitable coupling partners for transmetallation in palladium-catalyzed cross-coupling reactions. Organoboron compounds were previously examined by Heck and Negishi, however, without much success. Heck even observed that boronic acids can be competent cross-coupling partners, but only when stoichiometric quantities of palladium are employed. In 1979, Suzuki, having recently returned to Japan from his postdoctoral studies with Brown, resolved this issue with a clever solution. He found that organoboron reagents can become excellent coupling partners for transmetallation when treated with stoichiometric quantities of a base. The base is required for the activation of boronic acids, which are Lewis acids. The transmetallation is effective only when this type of boronate complex is formed from the reaction of the base with the organoboron reagent. In fact, the base normally plays a dual role. In addition to the activation of boronic acids, it activates the palladium-2 intermediates by substitution of its X-type ligand, which is normally a halogen. Now let me describe the factors making Suzuki coupling special. First of all, boronic acids, including different hybridization states of the carbon, are readily available. There are many relatively mild methods for the regioselective hydroboration of olefins and acetylenes. Aromatic systems also can be effectively borylated using either Miyaura borylation or direct CH borylation enabled by iridium catalysts. The resulting organoboron starting materials are easily handled and usually are stable under air and in the presence of moisture. Carbon atoms in all hybridization states can undergo carbon-carbon bond-forming reactions when using Suzuki couplings. Last but not least, typical Suzuki couplings offer mild and convenient reaction conditions and demonstrate remarkable functional group tolerance. In fact, the functional group tolerance of the reaction is indirectly controlled by the inorganic base used. A hallmark of the Suzuki discovery was the demonstration that bases can activate organometallics based on metalloids, allowing the coupling of organometallic reagents unable to undergo transmetallation under standard conditions. This discovery pointed to the possibility of uncovering coupling reactions of other organometallics with lower electronegativity differences between the metal and the organic moiety. Building on this knowledge, in 1988 Hiyama and co-workers described the palladium-catalyzed coupling of organosilanes with aryl halides and triflates. For the activation of organosilanes, they applied a number of fluoride bases, including cesium fluoride. The Hiyama coupling provided a more environmentally friendly and safe approach than other couplings, as the main byproducts of the reaction are silicates. The 90s witnessed the evolution of non-carbon-based nucleophiles participating in a cross-coupling process, thus adding new dimensions to palladium-catalyzed processes. The first palladium-catalyzed formation of carbon-nitrogen bonds was disclosed by Mijita and co-workers in 1983. The major limitation of this method was the use of stoichiometric amounts of toxic, as well as heat and moisture-sensitive tributyltin amide reagents. In 1995, Buchwald and Hartwig independently replaced the Mijida-amido-10 reagent with a free amine. The reaction was effective exclusively with bulky phosphine ligands and only worked in the presence of strong, bulky bases, such as lithium bis trimethylsilyl amide and sodium tert butoxide. The mechanism of the reaction is slightly different from the couplings involving organometallics. The oxidative addition step is followed by coordination of the amine to the palladium-2 intermediate as an L-type ligand. The coordination increases the acidity of the amine, which is being deprotonated by the base and turns into an X-type ligand, amide. The final step of the process is the reductive elimination of the aryl amine and regeneration of the palladium-0 active catalyst, which enters another cycle. To sum it up, in this lecture, you were introduced to the main classes of cross-coupling reactions. I presented a historical perspective on the three main waves of developments in this field, which is still underway and presently is focused predominantly on the development of novel catalytic systems via rational design and well-tuning of ligands controlling the activity of palladium catalysts. These and other relevant topics will be described in the following lectures of the module. Thank you for your attention.